Hello, this video is on lesson 8-1 and it begins on page 121 where we are going to begin talking about complex numbers. Okay, so one of the first things I had my students do is to simplify all perfect squares. And so my students were able to know this off the top of their head, and they answered these correctly. Now, the first thing I'll ask my students after they answer this is, why are these all called perfect squares? Well, if I take the square root of 3, what is that going to give me? So I go to my calculator, take the square root of 3, and it turns out that I don't get a whole number, I get a decimal, 1.73, and so on. Now, the reason these answers above are called perfect squares is because I get exactly a whole number for the answer. All of these numbers here are whole numbers. And so a perfect square always gives you a whole number. And so perfect squares are going to be coming up later, so it's important to know the first few perfect squares. And also, another thing that I wanted to get my students used to is basically when you're trying to answer the square root of a number, for example, the square root of 4 equals 2. Another way of looking at this is 2 squared is equal to 4. So in order to answer this question, you were basically asking, what number, when I square it, gives me 4? And so we know that the answer is 2. But actually, there's actually another answer instead of 2 that also gives you 4 when you square it. And so I had my students think about this. What could it be? What else could it be that when I square it, it also gives me 4? After a while, they were able to tell me that the answer is -2. And so the square root of 4 can also be equal to -2. We can have a positive and the negative answer. And so in order to reflect this idea, we just basically put plus or minus 2. And this is an idea that I want my students to get used to. For every time they take the square root, the answer should have there should be 2 answers, where one is positive and the other one is negative. So plus or minus for all of these. Okay, so on page 121, the learning targets are to know the definition of the complex number I, know that complex numbers can be written as a plus bi, where a and b are real numbers, graph complex numbers on the complex plane. Okay, so I had my students work these 2 equations that we see here, and one of the first things I wanted them to do is to solve this. And going back to the box method, we can use the box method to solve this really quick by factoring. And so this would have to be factors of 1 that give me 0, r1, and -1. So here we have x, and here we have -x, -1 plus 1. And so my factors would be x minus 1 and then x plus 1 equals 0. We go ahead and use the zero product property. And here we have x equals 1 and x equals -1. Alright, so we were able to solve this pretty easily. Now, what about the next equation? Let's go ahead and see if we can solve it using factoring. So first of all, you take the coefficient of x squared and the constant, multiply them together, basically 1 times 1. Now you want to find the factors of 1 that give you 0, because that's the coefficient of x. 1, 1, negative 1, 1. These are the only factors of 1 that I can come up with. So when I add these together, I get 2 and negative 2. And as it turns out, I can't have any factors of 1 that add up to give me 0. So how do we go about trying to solve this then? Well, this is where imaginary numbers come in. Instead of using factoring, let's just solve this using as a normal algebraic equation. So if I was just going to solve for x using algebra, I would subtract 1 from both sides, and then I get x squared is equal to negative 1. And what I'm going to do is I'm going to take the square root of both sides, and what I get is x is equal to the square root of negative 1. Plus or minus. So every time you take the square root, you always have to have plus or minus. Now, what is going to be the square root of negative 1? Let's put that in the calculator, see what we're going to get here. So negative 1 1 is going to be negative, and let's go ahead and see what happens when we take the square root. It is not a number. So the calculator is not going to help us there. Now the reason the calculator says it's not a number is because it's not a real number. The square root of negative 1 is not a real number. And so now we have to introduce the idea of what I is. What is the definition of the complex number I? Well, this is something that we just have to remember from now on. The square root of negative 1 is equal to I. This is the definition of I. Now, what is I? I is just a symbol. A symbol just like pi. Pi is equal to the circumference of a circle divided by its diameter, which, if you calculate that, should be 3.14159 and so on. Pi is just a symbol. It represents an idea of the circumference over the diameter. Same thing with I. I is a symbol that represents the square root of negative 1. And so just like we remember pi is equal to this, now we have to remember that I is equal to the square root of negative 1. And so that's the definition of I. Okay, what I want to ask you now is, when we solved this, x squared minus 1 equals 0, we found that the answers were x equals 1 and x equals negative 1. And then when we solved this, it turns out that it didn't have any real solutions. Instead, it had x equals I, which is a complex number, and x equals negative I. And so these equations look very similar. How can we tell why is it that this equation here has real solutions, x equals 1 and negative 1, and this equation here has imaginary solutions, complex solutions, which are not real numbers? What is basically the difference between these two? Well, a really intuitive understanding is by looking at the graph. And so if we take a graph, if you graph these on your calculator, and I take x squared minus 1, my y-intercept is going to be at negative 1, and it's going to be in the shape of a parabola. That's the best drawing I can make right there. There we go. Now, let me graph the other one. And notice that the y-intercept is going to be at positive 1. Here we go. Now, what are the difference between these two graphs? They both have a y-intercept, but what else do you see? And my students were able to notice that this crosses the x-axis 2 times, and this does not cross the x-axis at all. And so that is exactly why this, if you notice, this is x equals -1, and then here is x equals 1. It's crossing the x-axis at 2 different locations, and so that is why I have 2 real solutions. And here, I'm not intersecting the x-axis at all, and that's exactly why I have complex solutions. Exactly why. And so when we tried to solve this by factoring, we couldn't find an answer because it does not intersect the x-axis. And so it actually does have an answer, but they're not going to be real numbers. They're going to be complex numbers. And so that's the reason why this one is complex and this one is real. All right. Now, before we get into this, I just want to point out that there is a law that whenever you take the square root of a number that has 2 factors, a and b, the rule is that since I have 2 factors, for each factor I can separate it into 2 square roots depending on how many factors you have. Since I have 2 factors here, I have 2 square roots. This is the law that I'm going to be using. Now there's something important. I know that if you have a negative number inside the square root, this law does not apply. But for the sake of teaching this in an intuitive manner, I'm just going to do this. When I take the factor of this, it's going to be -1 times a times b, and I'm going to separate that into 3 different factors, 3 different square roots. I know this is not mathematically correct, but for the sake of teaching it, in order to be intuitive, I'm going to use that example. All right, thank you. So now if we go ahead and try to take the square roots of these negative numbers, well, the square root of -1, we just found out that that's going to be I. What about the square root of -9? Well, if we look back at our perfect squares, we got that the square root of 9 is equal to plus or minus 3, or just 3. What I'm going to do here is find the factors of 9. In other words, the square root of -9 is the same as -1, the square root of -1 times 9. That's exactly the same thing. Now, since I have 2 factors, 1, 2, that means that I can go ahead and separate this square root into 2 square roots, where in the first one I have -1, and in the second one I have 9. So for each factor I separate it into its own square root. And now notice that the square root of -1 is I. And so we have I, and then 9 is a perfect square. The square root of 9 is going to be 3. And so the answer is I3, or 3I. This is exactly the same thing. So can you see how we're still basically got kind of the same answer as this, except because it's negative, that negative becomes an I in my final answer. Let's do another example. Here we have the square root of negative 17, and this is going to be the same as the square root of negative 1 times 17. And since again I have two factors here, I can separate it into two different square roots. And again, I have the square root of negative 1, which is I. And notice that the square root of 17 is not a perfect square because it is between 16 and 25. And any numbers in between 16 and 25, those are not perfect squares. And so, because it's not a perfect square, we're just going to leave it the way it is. And as you can see, we get I square root of 17. So notice, every time you have a negative underneath the square root, it becomes I, outside the square root. And so, once we take out I, the negative goes away. It basically becomes I. Okay, let's do one more example here. Here we have the square root of negative 120, which I can separate as square root of negative 1 times 120. But here's what you want to do. Does 120 contain any factors that are perfect squares? And a really easy way to find out is look at your perfect squares. 1, 4, 9, and so on. And so, of course, every number has a factor of 1, so we don't want to check for that. We want to check to see if it has a factor of 4, because it's a perfect square. And so let's go to 120, take our calculator, 120, and we want to divide it by 4. And as you can see, 120 can be broken off into 4 times 30. So here's what we have. The square root of negative 120 becomes the square root of negative 1 times 4 times 30. Now, 30 does not contain any factors that are perfect squares, and so we're going to leave it just like that. And so what we can do now, since we have 3 factors, I write 3 square roots for each factor: the square root of negative 1, the square root of 4, and the square root of 30. Again, the square root of negative 1 is I, square root of 4 is 2, and then we have the square root of 30. And here is my final answer, which is also the same thing as 2I times the square root of 30. Either one is the correct answer. Okay. So what I had you do is, try these A, where you write each number in terms of I. Okay, let's go ahead and take a look at number 8 here. Simplify each of these expressions. Negative square root of 20 and the square root of negative 20. Okay, so negative square root of 20. 20, does it contain any perfect squares? Yes, it contains 4 and 5. And we know that 4 is a perfect square, and so we can rewrite this as negative 1. This is basically negative 1 on the outside. So negative 1 times the square root of 4 times 5. And since we have 2 factors, this is going to be the square root of 4 times the square root of 5. And we basically have negative 1 times 2 times the square root of 5. 5 is not a perfect square, so it's just going to stay like that. 4 is a perfect square, which means that it equals 2. And my final answer is negative 2 square root of 5. Alright. Now let's go ahead and do the other one. where we have the square root of negative 20. So the first thing I want to do is separate all the different factors. I have negative 1 times 4 times 5. Since I have 3 factors that make up negative 20, I write a square root for each one of them. And again, we have the square root of negative 1, which is equal to I. So we have I, square root of 4 is 2, times the square root of 5. And so I like rewriting it like this. The answer is 2I square root of 5. So notice, because in my first one, the negative was on the outside of the square root, that negative basically stays on the outside. Nothing happens to it. If the negative is on the inside of the square root, that negative becomes an I outside. And notice we no longer have a negative inside the square root. So that's a very important difference between these two expressions right here. These are not the same. Okay, and of course you could have gotten more practice doing 9A, B, C, and D. Alright, now we get introduced to the idea of a complex number. A complex number is a number in the form of a plus bi, where a and b are real numbers and I is equal to the square root of negative 1. Again, we see this. The set of complex numbers consists of the real numbers and the imaginary numbers. A complex number has two parts, the real part A and the imaginary part B. For example, in 2 plus 3i, the real part is 2 and the imaginary part is 3. So something very important here is that, let's take this for example, 2 plus 3i. The number that does not contain I, that is the real part. The number that is next to the I, is called the imaginary part. Now something important here is that the imaginary part does not include I, it's just the number next to I. So here the imaginary part is 3. So let's do C for example. If I write C down here, here's C, I square root of 10, what is going to be my imaginary part? Well, that's whatever's next to the I. In this case, it's going to be square root of 10. Square root of 10 is my imaginary part because it's right next to the I. So what is going to be my real part then? The real part, since we don't see any number, any constant, it's basically going to be 0. Because this can be written as 0 plus I square root of 10. 0 is going to be my real part. Even though we don't see it there, we have to understand that that's what the real part is going to be. So for each of these, just so you get a good understanding, the real part here is 5. The real part here is 0 plus 0. The real part here is 8, and the real part here is 5 over 2. Now if we wanted to identify the imaginary part is 8. The imaginary part here is the square root of 10. The imaginary part here is 0. And the imaginary part here is 3 over 2. Okay. Notice that the imaginary parts here do not include I, it's just whatever's next to the I. Here 8 is next to the I, the square root of 10. 0 here, even though we don't see that, it's going to be 0 is the imaginary part, and here it's going to be 3 over 2. Okay. So now that we have an idea of what complex number is, let's go and begin graphing complex numbers. Complex numbers in the form a plus bi can be represented geometrically as points in the complex plane. The complex plane is a rectangular grid similar to the Cartesian plane, with the horizontal axis representing the real part a of a complex number and the vertical axis representing the imaginary part bi of a complex number. The point AB on the complex plane represents the complex number a plus bi. Okay, so this is actually very, very simple. If I take a look at this, a plus bi, again, the real part is going to be a, and the real part, that number determines how if I move to the right or if I move to the left. The imaginary part here is b, and the imaginary part on the complex plane determines if I move up or if I move down. And so if we take a look at point A, the real part is 0. That means I'm not moving left or right. I'm just going to stay right at the origin. And since my imaginary part is 4 and it's positive, it tells me to move up 4 units on the vertical axis. And so here's my point. Point B, again, my real part is -3. That tells me to move 3 to the left, 3 units to the left. So 1, 2, 3. And then my imaginary part is 2, +2, which means I'm going to move up 2 units. And that is where B is going to take me at. C, 1 is my real part, so that tells me to move 1 to the right. And since my imaginary part is -4, that tells me to move down -4. Again, D, 3 is my real part, which means I'm gonna move 3 units to the right on the real axis, and my imaginary part is 0, which means it doesn't move up or down. It's just gonna stay there, and that's where point D is at. All right. As you can see, it's very simple to graph imaginary complex numbers on the complex plane. And I had you do some more practice here. We'll just go ahead and do these real quick. So 2 plus 3i. 2 is my real number, which means it's going to go 2 on the real axis. And then 3 is my imaginary part, which means I'm going to move up 3 on the imaginary axis, which is going to be here. Here's that point. 2 plus 3i. Here I have -3. It's going to be my real part, -3. And then -4 on the is going to be my imaginary part, which means I'm going to go down 4 units. And here is -3 minus 4i. Okay, so that's basically it for lesson 8-1.